Hello, my name is Kevin Murphy, and I work in Kubrick in Cardiff University in Wales. And today I'm going to talk about cerebrovascular health measures. And here we're going to combine fMRI and physiological signals to look at cerebrovascular processes. Okay, first of all, cerebrovascular health. Why is it important? Well, when neurons fire, they consume oxygen. And what happens is that smooth muscles in the arterioles dilate to bring in more blood flow to that area of the brain. So this process is called neurovascular coupling. And for it to work efficiently, the brain's vessels must function effectively. And you need to have then good cerebrovascular health, so good vessel health in the brain. So what can go wrong? Well, you can have large-scale things like strokes, so like ischemic strokes, TIAs, hemorrhages, aneurysms, and then blockages of certain larger vessels like stenosis and plaques. You can have things like different conditions like hypertension, hypotension, increased intracranial pressure. They'll affect the blood flow to the brain. And then you can have arterial stiffness, and so this is like a reduced smooth muscle function, so the smooth muscle doesn't work as well, and this here will show you then that it increases pulsatile energy to the blood, so you can see that normal elastic arteries buffer a cardiac pulse, so by the time it gets to the capillaries there's no pulsatile flow. But with stiff arteries you end up with a pulsatility in the microcirculation. And this can then lead to blood barrier breakdown, which obviously affects then the vascular function around the neurons. And then this then is all linked then to the lymphatic system and reduced waste clearance efficiency. So if your vessels aren't working properly, you can't clear away the waste well. And so all of these problems with cerebrovascular health, they can lead to neurodegeneration, and things like dementia and Alzheimer's disease are key issues. So fMRI, how does fMRI work? Well, you have neural activity, it consumes oxygen, it takes oxygen from the oxyhemoglobin, turns into deoxyhemoglobin. Then you have an increase in blood flow caused by the dilation of the vessels, which essentially washes out the deoxyhemoglobin. And so what you have is two different magnetic properties of oxy and deoxyhemoglobin, and that's what the bold signal is actually sensitive to. So it's the blood oxygenation level dependent signal. So this means that bold fMRI is a vascular signal, not a neural signal, and as is all the other ASL and vaso, other blood-based measures and functional measures in MRI. And so changes then in cerebrovascular health, so the health of the vessels and their ability to function, will alter the bold signal, and then that will modify then the relationship with neural activity. So you can see this in the literature, like here, Claudine Gauthier was comparing younger and older people and showing that the younger people have a higher bold signal to a task than the older people. Now the question is this related to actual neural activity, or is it because there's stiffer vessels in the older people and so it's responding less to the same neural activity? Blood pressure can change things here. We have James Coulson has done an experiment where he's looking at the mean arterial pressure, so the blood pressure in each person, their baseline blood pressure, and it correlates with a change in the bold signal in the brainstem. So the question is it related to neural activity, or is it related to the fact that the blood pressure is different? And finally, this is a paper from 20 years ago. Cohen was shown that by increasing or decreasing baseline blood flow using hypercapnia or hypocapnia, you see differences in the size of the bold response. And so the question then is that, like, are those differences really related to neural activity, or is it because the baseline blood flow is different? So these are the reasons that you would want to measure cerebrovascular health. And this is linked to physiological noise correction. So physiological noise correction removes the non-neural confounds. So that's anything that's related to vascular processes. But so instead of throwing this noise away, it can be used then to provide information about cerebrovascular health. And so if you're interested in these cerebrovascular health measures, what you do is you challenge the vascular system in the brain, and then you measure the results with fMRI to tell you something about how healthy the blood vessels are. So Within the brain, then there's like two kind of main vascular physiological processes, which I'm going to talk about through the rest of this talk. There's cerebrovascular reactivity, or CVR, and this is the dilation response to a vasoactive stimulus. So it means how much do the vessels dilate to a stimulus, and one of the main ones we use is CO2 in the bloodstream. Cerebral autoregulation, or CA for short, is the brain's ability to maintain a constant blood flow despite changes in systemic blood pressure. So when your blood pressure changes, your vessels try and buffer those changes to give you a constant blood flow within the brain. So these are the two processes that we'll discuss further and ways of measuring them. So just to go further and to explain a bit more, here we are looking at cerebrovascular reactivity, so CVR, and a CO2 inhalation test. So what you do is you put a gas mask on someone in the scanner, you give them CO2. This increases their end tidal CO2, which is essentially the amount of CO2 in the arterial blood. And as the CO2 goes up, your blood flow goes up. And what you find then that if you have poor cerebrovascular function, the amount that goes up will reduce. So that's one type of CVR task, but there are others, breathing variations. Then there's like drugs, acetazolamide, and then dietary things like nitrate and nitrites. Cerebral autoregulation, CA, as I said before, is the ability to keep the same blood flow despite your change in your arterial blood pressure. And here I'm showing a lower body negative pressure box, which I'll explain more later. But essentially, it can change your blood pressure. And there are other methods to do this as well: tight cuff release, forearm grip, and then various blood pressure drugs. So these are the two mechanisms that we're going to try and probe with fMRI. So first of all, measuring CVR, so cerebrovascular reactivity, with a CO2 challenge. Here is a paper from Molly Bright just showing the different CO2 traces from people. So their end tidal CO2, the amount of CO2 in their bloodstream when we've given them a task. And what you can see is that you can create a step design type end tidal CO2 by giving people gases, and that looks quite like a task in fMRI. Richard Wise back in 2007 was showing how you do a fixed inspired challenge, and you can then see fit the grey matter signals with that CO2 type trace. And here, this is just comparing two different types of method of supplying the CO2, and they give similar results. And then back in 2009, this shows that it doesn't really even have to be a long block of CO2. Normally we do a long length of CO2, but here, for example, in a 1 minute block of CO2, so CO2 for 1 minute, air for 1 minute, you can see this sinusoidal type shape, and you end up with a CVR map, which looks fairly similar. So one of the issues with doing CO2 and supplying CO2 is that you have to give gases, and it's difficult to set up, and it may be problematic for the people who are taking part. They might not like it. And so there's been a lot of focus then on using different ways of changing CVR. And one of them is through breathing variations. So this is just trying to change the end tidal CO2 by doing something with the way people breathe. So breath holds is a key one that people use. Kastrup back in 2001 showed that, like, if you hold your breath, they're holding their breath during this checked period, you can see a change in bold signal related to the breath hold. And that change then was correlated highly with a change caused by a CO2 inhalation. So the breath hold and CO2 can give fairly similar results. Then Schouten in 2008 showed practically that paced breathing and end expiration give better repeatability. And so what I mean by that is you tell someone to breathe in and breathe out, breathe in and breathe out. So you pace their breathing. And then at the end of the breathe out, you tell them to hold their breath. And at the end of that breath hold, then they have to exhale so that you can measure how much CO2 is in their blood. And then they have a recovery period, and then they start pacing your breathing again. And this then gives you the most repeatable breath hold response in the brain. And Molly Bright and myself back in 2013 showed that it didn't matter how long you held your breath for, or if you varied the length of time you held your breath, if you measure that CO2 properly, you can then get very similar CVR maps throughout the brain. So this is, again, how well the vessels are dilating throughout the brain. And this then can, like, I've used this, this is an example of with Fatima Garren Mayo, where we've used this in breath holds in stroke, and we're just looking at healthy tissue, and we're looking peri-infarct and lesion tissue, and you can see that the CVR basically reduces in these different areas. So it's showing you that the blood vessels themselves are not responding as well in the lesion and peri-infarct area as they are in the healthy area of the brain. So this is we were talking about increasing CO2 with breath hold, but there's another way of changing CO2, and that's reducing CO2 in your bloodstream. And acute deep breathing is one way of doing this. And essentially, this is a hyperventilation. You get someone to breathe heavily, and they'll blow off more CO2 and just reduce their CO2. And here, Molly Bright back in 2009 compared acute deep breathing and breath hold and showed that you get very similar results between the two. So the point is that you get some sort of variation into the end-tidal CO2 trace, so that you can actually measure the bulb signal change caused by it. So are there other ways of doing it? Well, recently, Pei-Ying Liu has shown that intermittent breath out modulation works quite well. So here you just allow people to breathe, and then you have a jittered task on period, basically, where they modulate their breathing in some way. Here it's just like a deep breathing for 6 seconds or 12 seconds, and she's compared that with breath hold and CO2. And what you get over here, for example, is that CO2 CVR, so CO2, the CVR caused by breathing in CO2 through a mask, is very similar to 6-second modulation. So this is another way of introducing variability into the end-tidal CO2 trace, which then causes variability in the bulb signal, which can then be measured in the brain. So then the question then is there enough variation in natural end-tidal CO2 fluctuation? So over time, your CO2 just naturally fluctuates, and maybe we don't actually need to disturb it at all. So back in 2004, quite early, Richard Wise showed that there's a natural changes in end-tidal CO2 here related to the bulb signal. And you can see it in particular areas of the brain, and these areas are basically areas with high blood volume. Ali Golestani showed then that you can look at different ways of actually analyzing this data and these natural fluctuations, and shown that you can use a cross correlation method or deconvolution type methods to show you very similar CVR type maps. And so it is possible to get some information from the natural fluctuations in end-tidal CO2. The real issue, though, is that there's very low signal to noise, and so moving these traces against each other, the bulb trace and the end-tidal CO2 trace, may sometimes not give you a good phase locking, because the signal to noise is so low. So this has then caused others then to go along and try and look at combining some approaches. So here, Rachel Stickland last year showed combining breath holds with a resting period, or acute deep breathing with a resting period, and then just looking at the rest itself, and showed then that you can get CVR maps with all these different conditions that are quite similar to each other. But the real benefit of doing this is that you get proper lag maps. So a lag is calculated from the breath hold or the acute deep breathing, and that then means that your CO2 is phase locked during the resting scan. And so if you try and remove then that CO2 as a physiological noise correction during rest, you get a much better map. Here is, I'm just going to talk about a slight aside. So calibrated bulb, the idea behind that, it removes the influence of CVR, and so calibrates the bulb signal so that it's closer to neural activity. And what you're actually trying to do is work out how much oxygen is being consumed. So the cerebral metabolic rate of oxygen. So here we have some equations. Don't worry if you don't really understand them, but what it's basically saying is that the bold signal change is equal to some maximum bold signal change, which you can use the CO2 experiment to calculate it, and then a change in blood volume, which is related to blood flow, which we can measure, and then OEF. And that OEF then can be converted into a CMRO2 map. And so this should be much more related to neural activity because it's removed all of the vascular components of the bold signal. Right, moving on then to cerebral autoregulation. So earlier on, I was telling you about cerebral autoregulation is the ability to maintain a constant blood flow despite changes in blood pressure. And here, there are much fewer papers in the literature dealing with this in fMRI. Here, Joe Whittaker from my lab used lower body negative pressure. So this is a lower body negative pressure box. It's basically a box that you seal around the waist and you suck the air out of the waist with a vacuum. And it causes blood then to pool in the legs. And that then changes your systemic tone and then should cause transient changes in your blood pressure. Now, one of the problems with this is that there's lots of issues with movement. And so people get sucked into this box. And so therefore, when we did this experiment, you had to wait until we couldn't do it during the transients, which meant then that there was no changes in blood pressure, but there are changes in blood volume. In that response, there are people trying to, the blood volume in the brain and the dilation of the vessels is trying to maintain a blood flow because of this task. And you can see that these are the areas of the brain that it works in. Now, there's like easier ways to do these sorts of things. One of them is measuring autoregulation with a hand grip task. So here, this is a paper from James Coulson, and he used the isometric forearm grip. So forearm grip is when you grip something in your hand, and you then try and get someone to hold it at 40% of their maximum grip power. And if you do this over time, and we're talking about over like a couple of minutes, you then get an increase in blood pressure, which then causes a change in the signal, which you can actually measure. And here, James showed that in the baseline blood pressure measure for each person is related to how much their bold signal changed in the brainstem related to that task. So this is this is showing you that cerebral autoregulation measures are dependent on the baseline blood pressure. Another method for use, one of the issues with the forearm grip is that there can be a lot of movement because people shake a lot when they're doing this. So we're trying to look at other ways of doing things. Tie cuff release is one candidate. Here, what you do is you put you put blood pressure cuffs around the person's thighs and you inflate them to above systolic pressure. So you hold it up for quite a while, like nearly 2 minutes, and then you deflate those cuffs. And when you deflate those cuffs, it lets that built up blood then back into the body. The blood volume goes down and you get this complicated shape of blood pressure where it goes up and down over time. And then you can measure that then in the fMRI signal change. And here, these are just maps showing you what's happening throughout the brain. Different areas respond at different times. And what's kind of interesting is that if you look at correlations in resting state correlations between different ROIs in the brain in a rest period and in this tie cuff release period, you get quite a high correlation. Now, in the tie cuff release, you would expect that just to be purely vascular. So it suggests that there is actually quite a lot of autoregulatory activity in the rest connectivity matrices. Again, now coming back to natural blood pressure fluctuations, so this is similar to the CO2 natural fluctuations. Is there enough variability in it to actually measure something in fMRI? So we look at beat to beat blood pressure here. Here you can see the gray matter signal and then the mean arterial pressure. And what we've done then is decompose it with a wavelet decomposition into different frequency scales. What then you see is that there's a correlation at around the 0.1 hertz frequency scale, which you may have heard of. It's quite a busy frequency window, which is a 0.1 hertz correlation between the mean arterial pressure and the fMRI signal. And this is lagged by roughly about 6 seconds, as you can see there. And what we've then shown is that this is actually related to R2 star rather than S0, which means it's related to blood flow rather than blood volume measures. And so it is something that is probably highly prevalent in the bold signal. So there are the different types of challenges that you can do to look at cerebrovascular reactivity and cerebral autoregulation. And so I just want to discuss a small bit the practical difficulties of doing these things. You may want to measure cerebral vascular health, but you need to understand that it's not the easiest thing to do. So first of all, there's participant discomfort, like for example, CO2 and masks. People don't like them. There can be lots of movement. I've kind of discussed that throughout the different tasks. Adverse responses. So some people may not respond well to a particular task, especially blood pressure tasks. And then you need monitoring needs. You need equipment. You need gas analyzers, O2 monitors, etc. You also need personnel. You need extra researchers, possibly clinicians, if that's what your ethics requires. There's time then to set up this equipment, and obviously then you need extra scans to actually give you some information to get the cerebrovascular health measures. Sometimes the cohort that you're interested in, it may not be able to do the challenge. For example, would you use a blood pressure manipulation in hypertensive participants? Maybe not. And then there's extra paperwork, it's ethics, risk assessment, and safety monitoring. But if you want to know something about cerebrovascular health, all of these things can be overcome. Here, I'm just looking at the pros and cons of different CVR challenges. So this is comparing the ones that we talked about. CO2 challenge, where you use the mask, gives its high signal to noise and good experimental control. However, there's lots of discomfort and it's difficult to set up and people may not like it. Breath holds and the other ways of varying breathing give less signal to noise, but they're less difficult to set up, less discomfort. They can cause a lot of movement. That's one issue, but there's chances of adverse responses are very low. And then the natural CO2 fluctuations, although it's low signal to noise, there is a bit of setup because you need to be able to measure CO2. There's no experimental control, but there's definitely no discomfort or more movement or adverse responses. And then looking at the cerebral autoregulation approaches, lower body negative pressure, it's a decent signal to noise. The setup, though, is very difficult. You can experimentally control it very well, but one of the biggest issues is movement. And we found like movement can be on the order of a couple of centimeters. So you really have to think carefully about how you design that experiment. The hand grip task, you can get quite high signal to noise. It can have a bit of movement though, and it's there's a bit of discomfort to it, but there's no real adverse responses because people can just stop if they don't feel great. And the tie cuff release, it's good signal to noise, good experimental control, good. It's good for movement, and that's one of the reasons why we're trying to think about using this more. And then your natural BP fluctuations, although it's good for discomfort and movement, it's a very low signal to noise. And so may not, it's quite a difficult thing to do, to disentangle the natural BP fluctuations from other fluctuations in the brain. So in conclusion, fMRI with physiological challenges can give you a comprehensive assessment of cerebrovascular health. So the physiological noise that the other talks in this session are talking about also contain a wealth of information about cerebrovascular function, and it's quite useful to have this information. And if you can combine those measurements of that cerebrovascular function with the standard fMRI measures, then you can boost the confidence that what you see in bold signal changes are actually related to neural activity and not changes in vascular reactivity. And this is especially important then in a group where you might expect a vascular difference. So with that, I'd like to thank my funder, welcome, and I'd like to thank you for listening.